Hello everyone, my name is Liviu Dănuț Vitan. I am an assistant professor at Politehnica University Timișoara, where I teach subjects of automation and SCADA systems. My research interest fields are electric drives and microgrids. So, in previous presentation, my colleagues introduced you to the hybrid DC-DC converters topics, and they presented to you different topologies that were developed by our team. In this presentation, I am going to show you two case studies of microgrids that were developed by us and how hybrid DC-DC converters are included in these structures. So let's begin. Okay, so this is the overview of the presentation. I will start it with a brief introduction to microgrids and their control. Then I will tell you the story of the starting point for our team in microgrid research, followed by the first microgrid case study, which is our research laboratory. This laboratory was developed to offer the necessary infrastructure for our research work in multiple fields. Then we will do a short visit, a virtual visit to the microgrid lab. And then I will present the second case study, which is a demonstration site of a DC microgrid having the dimension of a nanogrid being for residential applications. Finally, I will end up with a low-cost solution for the implementation of a wind turbine emulator with experimental results for validation and a recording of its operation. The wind turbine emulator is integrated into the microgrid lab. So, what is a microgrid? A microgrid can be defined in many ways, but a comprehensive definition can be as follows. A microgrid is an innovative control and management architecture at the distribution level, which makes it easy to implement smart grid techniques at power distribution level. A microgrid includes distributed energy resources, controllable loads, bidirectional power flow, communications and information technology in order to obtain maximum efficiency and reliability, isolated mode operations or on-grid mode operation, and so on. So this microgrid concept can be applied in both the AC and DC system. However, the implementation of the DC microgrid simplifies and provides the opportunity to integrate the renewable energy resources without converting in AC and intrinsically having higher efficiency. Moreover, the loads used in buildings, as you may know, may be DC loads, considering that in our days almost all of them convert AC power into DC power. So here is a representation of a conceptual layout of a microgrid, including a microgrid central controllers and local controllers. As I said earlier, a microgrid refers to a power distribution system integrated with distributed energy resources. As you can see in these figures, like PV panels, wind turbines, and storage if is considered in discharging mode. And also controllable loads like electric vehicles, again storage if is considered in charging mode, and typical loads. Now, the microgrid can either operate with the main grid or use distributed energy resources to supply the loads for isolated operation mode. It can be viewed as a small-scale grid, and it's widely considered one of the key components to integrate renewable distributed energy resources and save transmission losses for efficiency. Also, we know that in a conventional power system, the power flow is in one single direction from a power plant to the loads via transmission and distribution networks. Now, as more distributed energy resources are installed, the bidirectional power flow is possible from the grid and to the grid. Also, the size of a microgrid may vary depending on the applications. For example, the concept of microgrid can be implemented as a smart home, a smart building, a smart campus, a smart city, and so on. Now, for energy management, communication is indispensable in a microgrid. For this case, you can see two ways of communications are available between the local controllers and the microgrid central controller. So here we have the classification of microgrids. The microgrids can be classified into three categories based on the type of supply system used by the distribution grid as follows: AC microgrid system, hybrid AC-DC microgrid system, and DC microgrid system. Next, we will discuss shortly on each type from this classification. So this is the first system, which is AC microgrid system. And in this figure, we have a representation of a typical structure of an AC microgrid system interconnected with a medium voltage system at the point of common coupling. The distributed generator units and energy storage system are connected at some points within the distribution network, as you can see here, in this place, in this point, and in this point. Part of the network consisting of the distributed generator units and local circuits can form, as you see, a small isolated AC electric power system. More exactly, an AC microgrid. So we have the first one, here we have another one, and here is the other one. During normal operating conditions, the two networks are interconnected at the point of common coupling, while the loads are supplied from the local sources. For example, from these renewable energy sources, wind turbine, PV panels, hydro turbine, and so on. And if there is necessary more energy, it can be supplied from the utility grid. If the load demand power it's less than the power produced by the distributed generator units, of course that excess power can be exported to the public utility. So we have the second system, which is a combination between an AC system and a DC system, and it's called hybrid AC-DC microgrid system. So in the upper part of the figure, we have the same AC system as previous one, but in the lower part of the figure, it's a DC distribution system. The AC and the DC buses are connected through interlinking bidirectional converters, this one. However, these connections create stability issues and requires controls algorithms to maintain the power quality. Also, the distributed generator units are connected to minimize the losses and according to their natural output power, which can be AC or DC. And as you can see here, in the AC system, we have the hydro turbine and the wind turbine, and in the DC system, we have the PV panels. So the last type of microgrid system is DC microgrid system. And in this case, both systems, as you can see, are DC system and are interconnected with the main supply at the point of common coupling without having issues related to the AC-DC connection. For example, the point of common coupling can be, for example, a high voltage DC transmission line, which is connecting offshore wind farm. Now, to fully exploit the potential of power electronic converters in the microgrids, a hierarchical control of microgrids has been developed in the literature, which can be observed in this figure. So three main levels of controls have been developed: primary control, secondary control, and tertiary control. These were developed first for AC microgrids and adapted over the years with different concepts from primary, secondary, and tertiary control in order to work for DC microgrids. The primary control is implemented strictly locally, as you can see, within the distributed generator system. In the DC microgrid, installation of more than one power source is common. So, therefore, how to manage the distributed generators to share the load proportionally to their rated power or to be more efficient is considered an issue. Conventionally, Droop control is preferred options in this control level, as it provides autonomous control features to the distributed generators in the presence of communication failures. It effectively deals with the load sharing among distributed generators connected on the same DC bus and provides reference to sub-control loops, which can be voltage or control loops. Also, the Droop control can be perceived as a virtual resistance connected in series with the converter on the DC bus side. The secondary control is mainly set in the microgrid central controller together with the tertiary controls, which can be remotely located to the distributed generators, and thus communications are required. This control generates voltage shifting signals to the primary control level with the aim to eliminate the DC voltage deviation caused by the primary Droop controls. Moreover, it's also possible to implement the secondary control level locally inside the distributed generators. The tertiary control takes responsibility of power management between microgrid and upper grids, and it also commonly referred to as the energy management system. Also, this tertiary control has to prepare dispatch schedules inside of the microgrid to achieve the optimum operation. Now, in more detail, the hierarchical control is implemented using mainly three types of controls: centralized, decentralized, and distributed. In a centralized method, a central controller is used to collect data from local sensors, to process the data, and send out commands to locally primary controllers. As the signals are always transmitted in one direction, communication has to be very reliable because in the case of an interruption of communication, the operation of the microgrid will no longer be possible. So for this reason, centralized control deal with low reliability and resiliency. So to enhance the resiliency of power sharing methods, decentralized and distributed control have been developed. Decentralized methods do not require any communications link between the converters and hence introduce higher reliability and stability. For this method, Droop control is the simplest decentralized method employed in the DC microgrids. For the distributed control case, each converter is equipped with a secondary controller cascaded by the primary control. A communication system is employed to share the voltage and current information of converters between all of them. In a simple distributed secondary control, it is a requirement that all of the converters have access to the information of all the others. This last approach may be complex and have lower resiliency. However, consensus strategy with a sparse communication network has been introduced, which can use neighboring converter information to reach an acceptable operating conditions. Furthermore, Another sparsely communicated control approach can fulfill the power management objectives by only employing the current information of the converters. Now, so far, this has only been a brief introduction to microgrids. I'm sure that some of you know a lot more about this topic, and maybe it is in your research fields. So I will end up and let me tell you how our team started to approach the DC microgrid. So the starting point for our team to approach microgrid systems, let's say the source of inspiration, was a paper presented by Professor Boroevich from Virginia Tech at Optim ACHEM conference in 2010, entitled Future Electronic Power Distribution System, a Contemplative View. In this presented paper, at that time, the authors tried to put their thoughts in an attempt to illustrate the possible research direction on microgrids and the impact on the future electric power system, especially in the presence of renewable energy resources. So, as can be observed in this figure published in 2010, a contemporary vision back then, but an actual structure in our days of power delivery in a residential home, the majority of electrical households functions depend on the power electronics to convert electrical power into the form and amplitude required by the source or loads. Also, we can affirm about this structure that it is an AC microgrid, or more precise, a nanogrid, given its dimensions. And we say that it's an AC microgrid due to the presence of the distributed generators as PV panels, wind turbines, energy storage if it's considering in discharging states, and of the energy control meter, which consists of a smart power meter used for trading the energy with the grid, and a breaker for operation in isolated mode. Now, thinking about the fact that households loads more and more contain power electronics converters that optimize their operation and boost up the efficiency, it is interesting to know that practically all electronic loads have two-stage power conversion, where the front-end converters consist of a rectifier, an electromagnetic interface filter, and often a power factor circuit. Now, so far, this structure represented something that can be achieved due to the PV panel's penetration. What determined our team to approach this field was this representative diagram of Professor Boroevich's paper, which envisioned that future residential home could be based on DC nanogrid architecture. Compared to a AC nanogrid, it's obvious that DC nanogrid brings many advantages, starting with fewer power converters, higher overall system efficiency, and easier interface of renewable energy sources to a DC system. What is more, consumer electronics, electronic ballast, LED lighting, and variable speed motor drives can be more conveniently powered by DC. Also, this operation in isolated mode is possible, and to have optimal energy management, communication between all the components is required, including the relation with the AC grid. So, on this slide, you can see a straightforward comparison between an AC distribution system and a DC distribution system, where the lower numbers of components for a DC microgrid case, considering of course the same loads and the same distributed generators, is noticeable. So that we can translate it in a higher efficiency for DC microgrids. Next, it's an extension of the proposed architectural concept of the nanogrid, extended hierarchically to form a bigger microgrid system, which in turn is interfaced to a higher level distribution, and so on. The resulting system is a hybrid mix between AC and DC architecture comprising pico, nano, micro subgrids that are dynamically decoupled and hierarchically interconnected to form an intergrid. Now, starting from this concept, the team decided to develop a similar DC microgrid, or more exactly, a hybrid AC-DC microgrid laboratory for research purposes with the following main objectives for the design. First of all, to have an open and reconfigurable microgrid architecture to enhance the possibility to test our proposed new solutions in terms of hardware and software. Second, to have real conditions of a microgrid where to analyze and test the proposed topologies of a hybrid DC-DC converter and let them for long-term operation to verify their reliability. And finally, to have a structure that can be operated in a safe condition, implemented partially with industrial equipment. So here is the microgrid lab location. It is located in University Politehnica Timișoara campus inside of the electrical engineering faculty, which is this building. Also, just for reference, the first microgrid site developed by our team and presented in part 4 by Professor Corne Octavian, it's located in Alba Iulia County, which is situated approximately at a distance of 250 kilometers from university, which is located in Timiș County, Timișoara city. Okay, so here we have the microgrid lab architecture. It consists of 4 main power supply subsystems: photovoltaic subsystem, wind subsystem, hydro subsystem, and storage subsystem, and one load subsystem. For power distribution were implemented 2 DC buses. One is a high voltage DC bus with a level of voltage of 400 volts, and the other one is a low voltage DC bus with a level of voltage of 50 volts. Also, a 3-phase AC bus with a level of voltage of 400 volts RMS was implemented. The entire system is fully configurable, as you can see, in terms of hardware and software. Each subsystem can be connected within each power distribution bus, which permits different microgrid structures configuration, which may include 1, 2, or all sources. This is possible because each system component has its own automation structure, maximum power point tracking strategies, and state of charge of the storage elements. The entire system is coordinated with a central energy management unit, which can communicate with all components. In the subsystem, distributed control strategies are implemented for the reliability. So now, at this moment, this is the configuration of the microgrid lab in a more detailed diagram. So the power supply unit, PV panels, and hydro are connected to the 400 volts high voltage DC bus. Actually, the level of voltage is around 350 volts due to the direct connection of the PV panels, the value for which the PV panels operate around maximum power point. Of course, this direct connection was done to eliminate a power converter. To establish the stability of the high voltage DC bus in case of a sudden increase or a decrease of the voltage level above the limits, an energy buffer, consists of a supercapacitor and a high ratio bidirectional DC-DC converter, which is more exactly the bidirectional hybrid switch capacitor, which was presented in part 2 by my colleague Professor Dan Julia. It's connected to the high voltage DC bus. The high voltage DC bus can deliver the power either to the low voltage DC bus through this DC-DC converter, only one way, or into the AC bus through this DC-AC converter, directly to the AC bus. The wind subsystem, as you can observe, can deliver the power also into the AC bus using this diode bridge rectifier and then this inverter, or can inject the power into the low voltage DC bus using this diode bridge rectifier and this hybrid buck DC-DC converter, which was presented also in part 4 by my colleague Professor Cornea Octavian. Also, as you can see on supercapacitor, it's used for sudden peak power attenuation. The main storage element, which is this battery bank with a capacity of 20 kilowatt hour, which is connected, as you can see, at the low voltage DC bus. The low voltage DC bus it's connected to the AC bus through these three output ports hybrid inverter, which is also used for supplying the local AC loads. So the power flow from the high voltage DC bus to the low voltage DC bus can be achieved either directly through this DC-DC converter or using the AC bus through this inverter and then using again this hybrid inverter. For the wind and hydro subsystem, we use hardware in the loop emulator because it's difficult to implement such real systems in the laboratory conditions. Also, over the years, all the developed topologies of hybrid DC-DC converters have been tested on this architecture, being placed in different positions, like here to discharge the supercapacitor, or between the high voltage DC bus and the low voltage DC bus, or to charge and discharge the batteries, and so on. The DC loads are not represented here, but these are connected at both DC buses and also on the AC bus. In the following, I will do a description of the microgrid laboratory subsystem. So the first subsystem is the PV conversion subsystem. The PV subsystem consists of two power supplies. As can you see, the PV panels, which are installed on the roof of the lab, and this emulator, which is a programmable DC power supplies, and it can emulate various IV characteristics and is useful also when weather conditions are not favorable. The other components are a DC-DC converter for connection with the low voltage DC bus, and this inverter for the possibility to inject the power into the grid. And of course, we have also batteries for storing capabilities. As you can observe, depending on the state of switches S1 up to S6, there are many configurations possibilities for subsystem operation. For example, if we take the actual configuration of the microgrid, where the PV panels are connected directly to the high voltage DC bus, then the switch S1 and S6 are closed. S4 and S3, S4 and S3 are in the third position, which means that we have a connection with the main grid. Or if off-grid operation is required, then S2 is open. This one. Another example could be if there is a requirement to harvest the maximum power from the PV panels, then the DC-DC converter, which has a maximum power point tracking algorithm implemented, can be direct connect to the PV panel. In this case, the switch S1 will be closed, S6 will be open, and S4 will be in the first position. The battery bank, which is here, it consists of 8 gel technology 6 volts batteries, each having a capacity of 480 amperes hour. The local automation strategy is implemented through a programmable unit, and the subsystem communicates with the central energy management controller using the Ethernet network Modbus TCP/IP protocol. Here in the left are a few details about the equipment that are used in this subsystem. So here we have the wind conversion subsystem. The wind turbine is implemented as a hardware-in-the-loop emulator, which consists of a real permanent magnet synchronous generator. The permanent magnet synchronous generator is the same generator as the one mounted on the real wind turbine from the microgrid site presented in part 4 by Professor Octavian Cornea. The hardware-in-the-loop emulator is implemented via an induction motor driven by an AC DTC inverter, which receives references from a controller where the wind turbine mathematical model is computed. The permanent magnet synchronous generator output power can be injected directly into the AC bus and then to the national grid, or can charge this supercapacitor via this hybrid back DC-DC converter. From the supercapacitor, the power can be delivered to the low voltage DC bus through this DC-DC charger in order to charge the batteries. 3 power ports converters can manage the storage energy in a bidirectional way in relation to the grid and the local AC loads. The structure of this wind conversion subsystem is hybrid. It's using industrial equipment and experimental models made by us. All components can communicate with the central energy management controller. I'll give you more detail about it later in the presentation when we will discuss about the low-cost implementation of the wind turbine emulator. So this is the third subsystem, which is the hydro conversion subsystem, and which consists of 3 emulators connected to 3 different unique generators. The emulators are implemented using asynchronous induction machines driven by bidirectional AC DTC inverters. The hydro turbine mathematical models are implemented using the DSpace control board, which sends the references to the DTC inverters. These drives can also emulate wind turbines based on the same previous principle. And moreover, being the inverter being bidirectional, the generators, which are this one, can be tested in motor mode. For example, for pumped storage hydropower applications and so on. So, as you can observe, each generator is connected to an AC DTC converter, which inject the produced power into the high voltage DC bus. These converters are from Danfoss, but their control board was replaced with another interface card that provides full control over the inverter IGBT's gate drivers, which allow us to develop new control strategies. Also, in this case, as you can observe, these two DC buses, the high voltage DC bus and the low voltage DC bus, are connected through the bidirectional DC-DC converter, more exactly the bidirectional hybrid switch capacitor converter, which I showed you previously that this converter was used for charging and discharging the supercapacitor, which was connected on the high voltage DC bus. But at the moment when this schematic was drawn, this converter was used to supply the high voltage DC bus for motor mode operation of the generator. Now, regarding the control of the microgrid lab, as you have observed, two control strategies were implemented in the microgrid. One is decentralized control for each subsystem, such as maximum power point tracking, power limiting, voltage and current references, drop control in different variants, mainly for hybrid DC-DC converters, and of course, other type. And a centralized control, which is used for monitoring and setting the parameters through a SCADA system for the entire microgrid. Also, of course, that we have tried distributed approaches for a few experiments, but at this moment, such a control is not in operation. All control systems were implemented in a digital form. Now, here we have some pictures from the labs. As you can see in this figure are the roof-mounted PV panels along with solar irradiance meters. In this picture, you can see the hydro conversion system, the DC-DC interface, and the PV subsystem. Also, here are the electric generators and the hardware in the loops emulators related to the hydro turbine. And more exactly, you can see these are the asynchronous machine used for emulator, and these are the special constructed generator. In this picture is the wind subsystem. Here is the emulator, but we will see in detail later. And this is the DC AC storage interface in relation with the AC bus and with the DC bus. So for the actual configuration of the microgrid lab, we don't have relevant acquired results for operating, only for particular cases where one or two subsystems were tested. Results showed by my previous colleagues. But I will show you some results obtained for this configuration, which were presented in 2017 at the Optim-ACEMP conference. First of all, as you can already observe, this structure is similar to the actual configuration presented earlier and have the same DC coupled configuration with two DC buses. One is high voltage DC bus and the other is the low voltage DC bus. The microgrid, as you can observe, it's supplied from two renewable sources, one being PV panels and the others wind turbines, which is in fact the wind turbine emulators. As I said earlier, the PV panels are connected directly to the high voltage DC bus due to the high voltage DC bus value being close to the maximum power point operation of the PV panels. The energy storage is implemented through supercapacitors and rechargeable battery bank. The bidirectional hybrid DC-DC converter is responsible for charging and discharging the supercapacitor from and to the high voltage DC bus. The hybrid DC converter works as a boost converter in one direction and as a buck converter in the other direction. The hybrid DC converter uses a nonlinear drop control method for charging and discharging the supercapacitor. The charge controller, together with the hybrid DC-DC converter, are responsible for maintaining the voltage on the high voltage DC bus at around 350 volts DC, based, of course, on the amount of energy available from the renewable energy sources. The charge controller links the high voltage DC bus, where the renewable sources transfer their power, with the low voltage DC bus, where you can see the batteries are connected. If the renewable sources cannot provide enough power, a hybrid inverter, which is connected to the low voltage DC bus, can take power from the main grid in order to charge the batteries. If the system, of course, is connected to the main grid. On the other hand, when too much power is produced by the renewable sources, the inverter can inject the surplus into the main grid. This hybrid inverter is also responsible for supplying the AC microgrid loads. As you can see, this microgrid has a local network based on Ethernet in order to ensure connectivity between converters, power meters and server for microgrid settings, data acquisition and monitoring purposes. So here are a few experimental results of the operation of this microgrid configuration. On the left side is the operation for different power consumption and constant power production. And on the right side of the screen is the operation for constant power load and variation of the power provided by the PV panels. So for the first case, all renewable energy sources generate energy. At the beginning, the DC loads absorbs all the available power, maintaining the voltage of the high voltage DC bus at 350 volts. The charge controller is not active because it's only start at 355 volts. And we can see that the input and the output current of the charge controller is 0. Now, when the DC loads receive the command to decrease power consumption, the voltage, as we can see on the high voltage DC bus, is raised. Then, as an immediately response, the hybrid bidirectional DC converter goes in charging mode and raise its current in order to charge the supercapacitor. We can see that the voltage on the supercapacitor is increasing. Now, as a reaction to the increase in the high voltage DC bus, and since they function at constant power, the currents of the PV panels and of the wind turbine generator are decreasing. Now, after about 5 or 10 seconds, the charge controller starts providing energy to the low voltage DC bus, as we can see of its currents increase. And then the energy is injected into the main grid and to the AC loads by the hybrid inverter, which we can observe that it increases its input current. Now, for the second case, the microgrid is supplied by both energy sources until the PV panels, as you can see here, receive a command to stop at the time equals with 5 seconds. The DC loads, as I said, it's set to a constant value during the entire test, consuming, of course, constant power. The wind generator also provides a constant power of approximately 800 watts. The voltage supplied by the wind generator is enough to maintain the high voltage DC bus at 350 volts. Hence, the hybrid bidirectional DC converter not activate, and the voltage on the supercapacitor is kept constant. The hybrid bidirectional DC converter will only activate when the voltage in the high voltage DC bus is above 365 volts. The fluctuation presented in the hybrid DC converters in the current are very small and of no consequence. The actual reaction of stopping the PV system, as you can see, it can be observed in the operation of the charge controller, which is decreasing the current. Due to this, the hybrid inverter will stop pumping power into the main grid and attempts to take energy from the batteries in order to compensate the energy in the low voltage DC bus. Now, because of the battery state of charge, the voltage on the low voltage DC bus has a variation, as you can see, which can be seen also in the voltage of the high voltage DC bus through the charge controller current. So these were a few experiments about this structure of the microgrid. And next, we will do, as I said, a virtual visit to the microgrid laboratory. So now I will take you to a virtual visit in the microgrid laboratory for a better overview and understanding of it. I will use an app which can be accessed by through this link via a web browser. The app was developed by our university during the pandemic lockdown. During the pandemic lockdown, it was developed for the students and more especially for the high school students who had and still have plans to enroll at the university.
Okay, so this is the app. It's like a game. Here we have the instructions how to play this game. And now we have to wait a little until it's loading, but should not should not last very long, as we can see. So first of all, we have to introduce our name. And then we have to choose which faculty it's in our interest to visit. We will choose electrical engineering faculty. And now we are inside of the engineering faculty. Is not the whole faculty. Here we can see it's a main amphitheater. And from this building, from this room, we can go and to choose which lab we want to visit. Here are only a few labs, but one of them is the microgrid lab. So we are going to the door, we click, and we enter in the lab. So welcome to the microgrid laboratory. This is the entrance to the lab. On the right side here is the main AC distribution cabinet for the AC bus and connection with the national grid. Near him, you can observe an active harmonic filter, which is used in different teaching classes or in research, of course. Now, as you have seen, in the lab are 4 main workstations which are related to the conversion system. 1, 2, 3, and the 4th one. The first one is the PV system. The PV panels are installed, of course, on the roof. And here you can observe the grid inverter, which is this red one, and the DC charger, that charge controller, which links the 2 DC buses, the low voltage DC bus and the high voltage DC bus. And the PV emulator, And also local storage here, which is different, this storage, it's different from the main storage of the lab, which is located in this cabinet. And when I refer at the main storage, I refer to those 8 gel batteries with a total capacity of 20 kilowatts hour. Now, the bench from the middle, it's used for testing the hybrid DC converters. Here you can see the bidirectional hybrid switch capacitor converters with another version near it of hybrid buck DC converter, which it's used in the wind turbine subsystem. Down here are supercapacitor from the high voltage DC bus, which are charged and of course discharged by this bidirectional hybrid switch capacitor converter, or of course by another converter when that converter is tested. Now the third bench is the hydro conversion subsystem, where you can see the Danfoss inverters, those three, that are used for the generators controls. Also, you can observe the replace control board, which is this one, that provides us direct access to the IGBT's gate drivers of the inverters. And here on this one is the original control board. The inverter from the middle is disassembled because at the moment when the picture was made, we needed some data regarding the internal capacitors, if I remember well. And here is the DoSpace platform used for developing the control for the generators, and of course not only. And you also can observe that communication between the DoSpace and the inverter, it's ensured through galvanic separation using fiber optics. Now, the fourth bench, which is this one, is for wind conversion subsystem, where you can see the wind turbine emulator together with the power electronics for harvesting the energy provided by the real permanent magnet synchronous generator. In this cabinet is the frequency converter, which drives the induction machine, together consisting the wind turbine emulator. Now, this larger cabinet contains the hybrid inverter that is used with the AC bus, with the national grid, and the low voltage DC bus, and also the hybrid buck DC converter with the supercapacitor and the DC-DC charge controller used for the second configuration of the wind conversion subsystem. So, from the permanent magnet synchronous generator, the power can be injected into the grid using this diode bridge rectifier and this inverter. This is first configuration, or a second configuration, which is in this cabinet, consisting of, again, of a diode bridge rectifier, of the hybrid buck DC converter, and the DC-DC charge controller to inject the power into the low voltage DC bus. Also, you can observe the SCADA system from which all the subsystems are controlled and receive references and so on. Of course, that each workstation and cabinet contains the necessary protection equipment. Also, you can observe, like here's voltage and current sensors here as well, and here. And these are used for control strategies and of course. And there are other equipment like oscilloscope, DC sources here, electronic loads, and so on. Also, a part of them are in the repository room, which is here on the left. Also, the lab has two more rooms. One is here on the right, and it is a room with soldering station, electronic components, PCBs, and so on. And the other room is here on the back, and here are the motor generator assemblies for the hydro conversion subsystem, together with the DTC inverters and other electric drives bench. Now, hope you have created an overview of the lab, and with this virtual visit, I will end up with the presentation of the microgrid laboratory, and I will continue with the presentation of the second microgrid case study.
So here we are with the second microgrid case study, which has been developed through a grant supported by the Romanian Ministry of Research, Innovation and Digitization. The project, it's called Smart Building Adaptable to the Effects of Climate Change. Now, the goal of the project was to build a reduced scale modular residential house entitled Experimentarium, which has to be suitable for different envelope configurations and to have power distribution in DC integrated with renewable sources and off-grid operations. Now, a few constructive details about the house. The experimentarium, it's a lightweight steel structure with recoverable foundations, as you can see here, designed, of course, for reuse. The thermal insulation was implemented using newly developed thermal insulation wadding produced with polyester fibers made from the recycling of post-consumer PET bottles. To determine the efficiency of the insulations, the house has been equipped with 56 temperature sensors, 14 humidity sensors, and 3 CO2 sensors. The experimentarium, it's located in Timișoara. This is the Timișoara city. It's the same city where the university is located. In the courtyard of the Research Institute for Renewable Energies. This is the courtyard of the Research Institute for Renewable Energies. This is the institute, and here you can see the house. Also, as you can see, this second microgrid is not far away from our university, which is here, and that provides us advantages in terms of implementation and monitoring due to the short travel time. On this slide are a few details about the Research Institute for Renewable Energies. And I can tell you that this was built by Politehnica University Timișoara through European funding. Also, it has 18 research labs, which cover 4 main research areas: mechanics, industrial chemistry, electrical engineer, automation, and computers. And here are more detailed research fields. Now, on this right side of the screens are a few pictures with the buildings, and from inside of the buildings with some microscope and other equipment. So this is the architecture of the implemented microgrid. And as I previously said, the electric power distribution implemented in the experimental model is in direct current, and we can say that it's similar to a smart nanogrid given its dimension. This model integrates 2 types of renewable sources of energy, wind and solar, elements for conversion and storage of the electrical energy, and distributed control and energy management through a SCADA system. Now, because it is proposed for residential applications, common electrical appliances are used and adapted for DC supply. Based on the know-how from the microgrid laboratory, also this microgrid has been developed and to having two DC buses, a high voltage DC bus, which is this one, having a value of the voltage of 350 volts, and a low voltage DC bus with a level of 24 volts. Also, a standard AC bus, it's implemented with a voltage with a level of voltage of 230 volts RMS. And this was implemented for AC loads and as a backup solution. Now, for harvesting the wind energy, a 1 kilowatt vertical wind turbine coupled through a gearbox with a synchronous generator, it was implemented. The electrical power provided by the synchronous generator is injected into the low voltage DC bus using this charge controller. At the beginning, the system was designed so that the power provided by the wind turbine system should be injected into the high voltage DC bus for having lower currents, and only have the DC excitation of the synchronous generator supply from the low voltage DC bus. But when we started the implementation, the only available vertical wind turbine on the market was with a charge controller on 24 volts. So that was the reason for having this configuration. The solar energy, as you can see, it's converted into electrical energy using 12 250 watts peak photovoltaic panels and an additionally 24 40 watts peak photovoltaic louvers. Both systems being connected to the low voltage DC bus through these two maximum power point tracking charge controllers. The energy storage, it's composed of four 12 volts 220 amperes hours valve regulated lead acid gel batteries, which are especially designed for a residential photovoltaic system. The battery can store approximately 10 kilowatt hour of electrical energy, which we can say that for a usual house, it's enough for maybe 1 or 2 days, depending on the loads. The batteries, as you can see, are connected to the low voltage DC bus for avoiding the high voltage DC requirements. The connection between the low voltage DC bus and the high voltage DC bus, it's done through this bidirectional hybrid switch capacitor converter. This bidirectional hybrid switch capacitor converter has capabilities of high ratio voltage conversion with high efficiency and we can say some low cost. More detail about it are presented or were presented in part 3 by my colleague Gerardo Mihaiță. The connection to the AC grid, as you can see, is done through this hybrid inverter, which has the DC output connected into the low voltage DC bus system. Also, the AC loads are supplied by the hybrid inverter, and from this AC bus, the high voltage DC bus can be supplied using this diode bridge rectifier. This diode bridge rectifier was implemented as a backup solution for an eventual failure of the bidirectional hybrid switch capacitor. And that's because this converter was developed and built by us, and of course that we are expecting to having some eventually issues with it. Now, regarding the loads, as I said at the beginning, common electrical appliances as an induction hub, a fridge, an air conditioning, and TV were adapted for DC supply and are connected, as you can see, at the high voltage DC bus. The conversion was not so complicated given the fact that all of them use a diode bridge rectifiers as an interface with the AC grid. I can say that there were some specific problems, especially for the induction hub, for which there was necessary to emulate the grid frequency. And that's because the grid frequency it's used by the internal zero voltage switching resonant converter to achieve a higher power factor. There are also loads on the low voltage DC bus as the lighting system, which was implemented using LED strips directly connected to the bus, the sensors measuring system for temperature, humidity, and CO2, also directly connected to the bus, and the automation and the SCADA system. The communication between all devices is ensured using Ethernet network protocol Modbus TCP/IP. The total number of devices that communicate and exchange information is 21, including the BHC converter, maximum power point charge controller, the synchronous generator controller, and so on. Now, this SCADA system supervises and controls the entire flow of electrical energy and ensures that the acquisition of all parameters. Now I will give you some detail about the management of this microgrid. This microgrid uses a decentralized control based on the voltage of the two DC buses, the low voltage DC bus and the high voltage DC bus, and the power through the bidirectional hybrid switch capacitor converter and through the hybrid inverter. The hybrid inverter offers two modes of operating: on-grid, which means connected to the national grid, and off-grid, which means, of course, insulated from the national grid. On the on-grid mode, if there is not enough power produced by the renewable sources and the batteries are at a low level, the hybrid inverter will supply power from the AC grid and delivers it to the loads and recharge the batteries. In the other case, when more power is produced and it's not required by the loads, the hybrid inverter can deliver the extra power to the national grid. At the moment, the house doesn't have a connection with the national grid, so this wire doesn't exist. So it's only operate in off-grid mode. In the off-grid mode, in case of lower production by renewable sources, the loads are prioritized and are supplied from the batteries, from these batteries. On the other hand, when too much power is available, if the batteries are already charged, then the energy production from renewable sources is lowered, or even some of them are fully stopped. For the initial case, when the wind turbine was supposed to be connected to the high voltage DC bus, each renewable sources will have reduced its power depending on the loads to have the lowest amount of power through the BHSC converter. The diode bridge rectifier will only provide power if the high voltage DC bus level of voltage will be lower than the AC bus rectified voltage, or another option is to be fully stopped using contactor for separation. Also, in this diagram is not presented, but on the high voltage DC bus, it's installed a capacitor bank for more voltage stability, and if only this diode bridge rectifier is used to supply the high voltage DC bus, at the first commissioning, the capacitors are charged using a resistor, which then it's short circuited. So next we have the SCADA system, which has been developed in LabVIEW software provided by National Instrument, and with objectives to be easy to operate and to understand, because most of the time this module, the experimentarium, it's dedicated and operated by students. So as you can observe in the upper part, here is the menu for navigation between the SCADA screens. So on these first windows is presented on the left side of the screen the block diagram of the microgrid, where we have the low voltage DC bus is this one, the renewable sources, roof photovoltaic panels, lower photovoltaic panels, and the wind turbines, the loads connected to the low voltage DC bus, and the batteries. Also here is the high voltage DC bus with the loads, the connection between the low voltage DC bus and high voltage DC bus, which is this bidirectional hybrid switch capacitor, and the backup solution, the diode bridge rectifier, which provide energy from the AC bus, where are also connected the AC loads, and the hybrid inverter, and of course the connection with the grid, but as I said, which is not active. These lines are moving according to the power flow. Also, several parameters are displayed, as you can see, the instant power, consumed power for this case, and produced power, the state of charger of batteries, and the voltage and the current. The current is negative or positive depending on the state of the battery, if it's charging or discharging. And here we can observe the operation of the inverters and other parameters. On the right side of the screen, you can see the daily production for each renewable energy. So here we have the daily production for roof photovoltaic panels, for the lower photovoltaic panels, and for the wind turbine. And this is the total energy production for all sources. Also, here we can see if somebody is in the module. And in this lower part, we have the control buttons for the lighting system and for the wind turbine brake. Now we cannot see, but when we press a button, the color will be blue, and this blue means that or confirms the transmission of the information and also its execution by the final equipment. Because you know, when you have an equipment with communications, maybe you can press the button, but you don't know if this step was executed. So if the color is blue, that means also the final equipment executed the command. Next, we have the second SCADA screen, where the detailed architecture of the microgrid is presented, along with more detailed electrical parameters for each equipment. Also, from this screen, the hybrid bidirectional DC converter can be enabled or disabled. The mode of operation can be set, manual or automatic. and references for the high voltage DC and low voltage DC bus can be also set. Also, diode bridge rectifier can be activate or deactivate. And as I said, we can see more details electrical parameters. For example, for the wind turbine systems, we can see the parameters before and after the charge controllers. The same thing for the roof PV panels and so on. So the other screens of the SCADA system, apart from last one, are dedicated to monitoring the temperature, humidity, and CO2 sensors. These screens are categorized as follows: east facade, north facade, west facade, south facade, and floor and interior. On this picture, you can see the position of the sensors and here how they are placed in the thermal insulation. So you can see that in the thermal insulation, we have 3 temperature sensors and 1 humidity sensors. Also, you can see the actual value of the temperature, and here is for humidity. And on this graphic are the historical data values which were stored with a sampling time of 1 minute, given the fact that the temperature is not so dynamic value. So here is the next screen, which is, as I said, is north facade. Again, with the position of the sensors, you can see that here are also sensors mounted on the roof, and with the same momentary values and historical data. The west facade, which is similar to the previous one. The south facade, again, the south facade has sensors mounted on the roof. And you can see, of course, the temperature. If we take, for example, these sensors, we have S1T, S2T, S3T. These represent the position in the thermal insulation layer. And this is the exterior, interior, middle and interior, and you can see the gradient of the temperature. The floor, here is the first floor slab, the ground floor, and the exterior one. And we can see that in outside the temperature is 32.8 degrees, and here is the ground. Again, we can see the gradient of the temperature and so on. And here are the interior sensors. On the first floor are 2 sensors, which are mounted at a distance of 1.5 meters to see again the gradient, but in this case was pretty similar temperature. Mostly in the morning and in the evening there will be a difference between them, but we can see a difference of temperature between the ground floor and the first floor, as expected, of course. And this is the last screen, which is dedicated to communication settings and other parameters, because I told you there are a lot of devices and IP address, registers, and so on has to be set. The screen it's longer in the downside part. Now here are a few pictures with the module. On the left side is the south facade. You can see the PV panels, the photovoltaic louvers. In the middle is the vertical wind turbine, You can see it here. And on the right side is the north facade. And back then when the picture was done, the air conditioning wasn't mounted, but right now it's mounted and it's positioned here. So here are a few pictures from inside of the module. You can observe the LED strips on the ground floor in these pictures and in these pictures, and on the first floor in this one and in this one. And some of the appliances like the fridge and the air conditioning. You can also see that the air conditioning it's connected to this small distribution box, and that's because being in DC distribution, dedicated outlet weren't available. Also, you can observe this distribution box like this one, this one, this one, and this one, and there are others too, in which are the devices for temperature, humidity, and CO2 sensors. And regarding the temperature sensors, you can observe the one from the ground floor, it's here. And also those two temperature sensors from the first floor that I showed you previously. One is here and the other is here. And here on the first floor are the electrical equipments, as you can observe. And we can see the charge controller for the PV, for the roof PV panels, the maximum power point tracking charge controller. And here is the other one for the PV louvers. This black one is the charge controller for the wind turbine. Here you can observe the batteries together with the management systems for the batteries. Here are some protections. This is the hybrid inverter, which is related to the AC bus and the connection with the low voltage DC bus, and also with the grid. But as I told you, the grid it's not available now. Here is one of the two switches which are for communications. Here are some measurement current and voltage sensors. And in this cabinet, you can observe the capacitor bank installed on the high voltage DC bus. And here are with white the charging resistors, this one, and this one. And given the fact that the implementation of the microgrid is underway, we can say almost 90% complete. The only missing part is the hybrid DC, the hybrid bidirectional DC converter, which will be placed in this empty spot from this cabinet. And also here you can see the TV. Being for research purposes is not so aesthetic in the interior, but of course that will be modified in the futures. So here we have some recent data regarding the energy consumption. For this data, only PV panels were used as energy sources because the other energy sources, wind turbine and PV louvers, were not functional. As I said, the commissioning is underway and they will be included soon. So in the upper part is the energy consumption overview for one day, more exactly 10 May 2023. There is no grid connection, so the amount of the produced energy, it's almost the consumed energy, the difference being given by the, of course, by the efficiency. Yellow bars will represent the produced energy, and these with red represent the consumed energy. This blue line represents the state of charge of the storage. And here, in the lower part, is the overview of the production and consumption energy for one full month, more exactly the April. On this slide, we have the energy produced and consumption overview for the winter months, and it can be observed that consumption is reduced in comparison with the consumption for April due to the lack of available energy. So in this case, the microgrid disconnected a part of the loads, prioritizing the important ones. In this case, being the acquisition of temperature, humidity, and CO2. Here is for January, and in the lower part it's for February. In February there was more days with available sun. And in this slide, it's a more eloquent comparison between summer and between a summer month and a winter month. So when there is enough available energy, the overall consumption will be around 100 kilowatts hour. But in case of lower available energy, like in December month, the system will reduce the loads and eventually will completely stop, of course, if there will be a longer period without sun. But we expect that with the commissioning of the wind turbine and PV lower panels to eliminate these gaps. Again, this is for the off-grid operation of the microgrid. Finally, the connection with the national grid will be available, and then energy trade with the grid will assure full operation of the microgrid. As regarding the consumed energy, these lower values, like 100 kilowatts per month, which we can say it's a lower value for a house, it's given by the fact that the air conditioning and induction hub weren't used. Until this moment, these were verified that are well functioning and have been started only a few times. We'll follow to establish a schedule for them to be automatically started by the microgrid automation system and to record their influence. But until now, the objective was to observe how the thermal insulation will behave with no external influence. Okay, so with this second case study, I end up the presentation related to microgrids, and in the next, I will present to you how we have implemented the wind turbine emulator with a low-cost device for computing the mathematical model. So we are back with the wind turbine subsystem, which is composed of the wind turbine emulator, which is this one, and two different configurations for harvesting the permanent magnet synchronous generator power. The first one use industrial equipment and inject the power directly to the AC bus, and the second one use this diode bridge rectifier and this hybrid back DC converter to charge this supercapacitor, and then using industrial equipment, DC-DC charge controller, deliver the powers to the low voltage DC bus to charge the batteries, or through this hybrid inverter to supply the AC loads or to inject the power into the AC bus. Here on the right side of the screen are the main parameters of each component. Okay, so first of all, why the need of a wind turbine emulator? It's clear that in laboratory conditions, it's very difficult to have a proper wind turbine, or moreover, to ensure the environment to create wind speed for the wind turbine operation. So the most appropriate solution is to use a hardware-in-the-loop wind turbine emulator, which can offer reproducible results under different conditions. Having a wind turbine emulator, the real parts like the generator, power converters, power extraction algorithms, and so on can be tested and then implemented on a real wind turbine. Also, it's very easy to be integrated in microgrid configurations for studying different control and strategies of the microgrid. The wind turbine emulator are usually implemented using different motor types for the emulator or different control platforms for the mathematical model. The most common platforms are DSpace and National Instrument Compact Rio. But these platforms have common disadvantages as high prices for hardware and software parts, necessary skills for programming, and not an easy commissioning procedure. Also, when it is used by undergraduate students, and not only, of course, there is a certain risk of being damaged by them, most commonly using too high voltage on analog or digital inputs. Now, to overcome these problems, we have thought, how about replacing the control platform with a more low-cost devices which can be easily replaced. So we have chosen to use an intelligent relay, which is similar to a programmable logic controller, a PLC, but with a low price. Of course, it has a lower performance than a PLC, but another advantage is that the programming software is free. I will give you later more detailed about it. So we started to develop the control algorithm for the intelligent relay using the first configuration of the wind turbine emulator, where you can observe that initially we use compact Rio platform for the mathematical model, but also DSpace have been used in other configurations. So we have the real wind turbine generator, which is a 5 kilowatts 120 RPMs permanent magnet synchronous generator. Again, I remember you that this generator is the same as the real one from the Chugud site presented in part 4 by Professor Octavian Cornea. For this turbine emulator, it uses a 3-phase square cage induction motor driven by a frequency converter which is fed from the grid. The frequency converter has the capability to control the speed or the torque through high performance vector control called or known as DTC, direct torque control. The shaft speed and torque are estimated with good accuracy, and the data are sent to the control platform. The induction machine is coupled with the permanent magnet synchronous generator through this gearbox with a ratio of 6:1 because of the higher speed of the induction motor, which is 730 RPMs. The electrical power provided by the permanent magnet synchronous generator is injected into the grid using this diode bridge rectifier and then this single phase inverter. Now, here is the same first configuration, but something more detailed schematics, where the compact Rio platform is replaced with the intelligent relay. So, from the frequency converter, as you can see, the torque of the induction motor is acquired, and together with the wind speed reference, which can be provided by a SCADA system or can also be internally set in the intelligent relay, and based on the mathematical model of the wind turbine, reference speed for the induction motor is computed and prescribed to the frequency converter. The communication between the intelligent relay and the frequency converter is done through an Ethernet network and using protocol Modbus TCP/IP, which simplifies the communications between them, having only one cable instead of 2 or 3 analog cables. Now, to better understand what are the challenges when we want to implement a wind turbine emulator, I will show you the used mathematical model of the wind turbine. So, modeling the rotor blade of a wind turbine is based on the conversion of the available power correlated with the speed of the wind into mechanical power. The equation that gives the available wind power in the area swept by the wind turbine blades is this one from here, where this term, ρ, is the specific air density in kilogram per cubic meters. A represent the blade swept area in square meters, and V represent the wind speed in meter per second. Now, this equation was obtained from the time derivative of the wind kinetic energy, considering the wind speed V to be constant, where m represents the mass, d is the distance, and t is the time. Now, of course that from the total wind power, only a part can be transmitted to the wind turbine shaft. In this case, the mechanical power that can be converted into electrical power is given by this equation, where this term Cp is the power coefficient of the wind turbine, which is a function of the tip speed ratio, this term lambda, and blade pitch angle beta. It is well known that the maximum theoretical value for it is 0.59, which is also known as Betz limit, which represents the maximum efficiency for a wind turbine. For low power wind turbines, usually blade pitch angle is constant. So therefore, the dependence on blade pitch angle beta is not taken in consideration in this model. So considering this, at each moment, the speed ratio can be calculated by this equation, where R represents the radius of the circle traced by the turbine blades, and omega is the shaft speed, and of course again V is the wind speed. Actually, the power coefficient is related to the torque coefficient, as can you see. The torque coefficient must be determined for each wind turbine design. For this wind turbine, the torque coefficient is computed from this equation, where these terms CT0, A, and B are constant obtained from the mechanical design of the wind turbine. Now, if we are replaying this term into this equation, the power coefficient becomes, as you can see here in this equation. So now, taking this power coefficient in the mechanical wind turbine power, we can obtain the wind turbine torque by dividing the wind turbine power at the shaft angular speed. So, resulting in this expression. So, this is the expression that has to be implemented, which for a dedicated computational platform, it's not a problem to be solved. But for the intelligent relay that I said that will replace a dedicated platform will be an issue. And we will see later why. Now, to be able to develop and run simulations for the entire system, the electrical model of the permanent magnet synchronous generator, of the diode bridge rectifier, and of the inverter are necessary. For the experimental implementation, all of these three parts exist, so their models are not necessary, but for simulations, they are required. So for the steady state regime, this is the equation which covers the electrical model, where this term is the numbers of pole pairs, this is the angular speed in radian per second, this one represents the linkage flux given by permanent magnet in Weber, Ls is the synchronous inductance in Henry, IFP is the peak phase current in amps, of course, RS represents the PMSG stator resistance, VDC is the rectified voltage, and VDB is the voltage drop across the diode bridge rectifier. The VDC is computed from these equations, where CF is the filter capacitance in farad, and ILoad is the load current given by the coupled load in the stator of the permanent magnet synchronous generator. Now, to obtain the angular speed of the wind turbine, the torque of the PMSG has to be calculated and is described by this equation, where these terms KPFE represent the core loss coefficient, which depends of the angular speed. And now, finally, to determine the angular speed of the wind turbine and of the PMSG, of course, the dynamic equation of motion is used, where J represents the total inertia of the wind turbine system and is the sum between the wind turbine and the permanent magnet synchronous generator inertia, as you can see here. So these are the equations which describe the entire system of the wind turbine emulator and were used for the simulation. As regarding the real implementations, only the equation that provide the wind turbine torque and the dynamic equation are necessary. The electrical model, this one, is not used because, as I said, all the equipment exists. So now let's see how the wind turbine emulator was implemented on the real bench. As I said, it's based on an existing 5-blade fixed pitch wind turbine, which has a rated power of 5 kilowatts at a rated angular speed of 126 RPMs, achieved for a rated speed of wind speed of 10 meters per second. And here are a few mechanical construction values. Now, based on the mathematical model and on the parameters of the wind turbine, the power coefficient Cp versus tip speed ratio lambda characteristic was computed, and it can be observed in this figure. Now, the power coefficient has a maximum value which is given at an optimal tip speed ratio, as you can observe here. On the right side of the screen are the wind turbine characteristics, power and torque versus angular speed, which were computed for the wind speed values between 0.5 and 10 meters per second. More exactly are 11 curves. Among the characteristics, it shows the load curve, this one, and here, implemented in the inverter. The load curve depends on the DC voltage, but being a permanent magnet synchronous generator, the DC voltage is dependent to the angular speed. The curve implemented in the inverter is slightly, as you can observe here, it's slightly deviated from the maximum power point of some characteristics, and that's to obtain an optimal regime overall, because the curve was implemented as a 4-degree polynomial. So, due to the reason that I mentioned before, we have chosen to replace the dedicated control platform with a lower cost options, which is this intelligent relay. In general, the intelligent relay have limitations regarding processing capabilities, usually being used in simple residential applications where handling with advanced computation is not needed. The intelligent relay used in this application is from Siemens, and it's called Logo 8. Now, what are the problems? First of all, this relay operates with 16-bit signed integers and does not have root and power functions. In addition, because of the very low value of the Winterbein coefficient, and given the fact that we operate with 16-bit integers, it's very difficult to implement the mathematical expression of the Winterbein power, because the obtained results for some of the iterations are completely out of range and unacceptable. So, if we look more closely to the dynamic equation, we can observe that the only important parameter from the mathematical wind turbine model is the wind turbine torque, noted previously with T WT. So with that in mind, the solution for implementation into the intelligent relay was to approximate the wind turbine torque characteristic with a third-degree polynomial. The third-degree polynomial is a good compromise between precision and computational requirements by the intelligent relay. In this figure, you can see a comparison between theoretical characteristics with blue one here, more exactly, and a polynomial approximation for a value of the wind speed equals with 9 meters per second. We can observe here, in this lower part, a small deviation from theoretical characteristics and the approximated one, which is at low speed. But it can be neglected because the loading curve of the inverter does not have a steady state operation point in that position, because the inverter will absorb the load current to go into the maximum power point operation. So now we have one polynomial for one characteristics which is available for a specific wind speed. The question is how many characteristics we should approximate. From multiple trials and considering the memory limitations of the intelligent relay, there were chosen 11 characteristics which were approximated, of course, with 11 polynomials. These characteristics are exactly those one presented previously on the previous slide. Okay, but the wind speed doesn't jump directly from 5 meters per second to 6 meters per second, or from 3 meters per second to 4 meters per second. There are also values between the characteristics. So to overcome this problem, linear interpolation between each two adjacent characteristics has been done, and has been found that this method offers a very good precision for the minimum number of 11 characteristics. The linear interpolation was implemented, or is given by these equations, where x1 and I1 are the wind speed and torque of the first characteristics, x3 and I3 are the wind speed and torque of the second characteristics, and X2 and I2 are the actual wind speed and the calculated torque. Here we have the architecture of the implemented software in the intelligent relay. The actual torque is acquired from the frequency converter as a percentage of the nominal torque of the induction machine. So we obtain the induction machine torque. Now, the permanent magnet synchronous generator torque, which is this term Tg, it's calculated from the induction motor torque, from this one, but considering the inertia of the hardware system and of the gearbox, which must be compensated. And it's compensated through this term Tc. Now, in order to calculate this term Tc, we have to calculate the total inertia of the hardware system, which is given in this equation, being a sum of the induction motor inertia, gearbox inertia, and generator inertia. Now, the gearbox inertia is calculated based on the gearbox inertia, where NGB is the gearbox coefficient. The compensation torque, now it's calculated in this equation using the dynamic equation and of course considering the inertia of the induction motor and of the gearbox. The speed derivative necessary for calculation of compensation torque is obtained from previously dynamic equation, and then the permanent magnet synchronous generator torque down here can be calculated. Now, the wind turbine torque, as you can see here, it's calculated based on the 11 polynomials and of course based on the interpolation equation. The actual speed of the induction machine estimated by the frequency converter is forwarded to all polynomials. Now, according to the wind speed, a selection, as you can see, is made between which characteristics are to be used for the interpolation. Further, this function block, is necessary when the mechanical components are not correctly aligned. The friction torque given by the non-alignment can be determined experimentally and added to the wind turbine torque or decrease, of course, from the permanent magnet synchronous generator. So we have the wind turbine torque, we have the generator torque, and all that remains is to apply the dynamic equation of motion in order to obtain the reference speed for the frequency converters with the observation that the inertia J was introduced in the integration time constant. And why was necessary to be introduced in the time integration constant? Because it is not possible to divide the difference between the wind turbine and generator torque to the inertia before the integrator, because at low values the results will be imprecise while working with integers, of course. Also, dividing after integrator is not a solution because the maximum value of the integrator of this chosen intelligent relay is 1000, which will give a calculated reference speed of 7.06 radians per second instead of, let's say, minimum of 10 radian per second, which is the rated speed of the wind turbine. Now, the constant time, this Ti, of the integrator, it's calculated using this expression where omega 0, it's the maximum angular speed, and AQ is the output of the integrator, and J, of course, is the inertia. Also, considering that the maximum angular speed of the induction motor is 730 RPMs, and the gearbox coefficient is 6.03, the maximum angular speed, omega 0, was set to 13 radians per second. This value covers the maximum power point of all wind turbine characteristics, so higher values can be neglected. This was in order to minimize or to have efficiency in the implementation program on the intelligent relay, and also to have a protection. It is not necessary to prescribe higher speed for the frequency converter if the wind turbine will not operate in that region. One last thing here, the reference wind speed V can be set from a SCADA system or locally from the intelligent relay using its functional key. It can be set to a specific value, or cyclic profiles can be used. So now some results. As I told you, in order to validate the experimental results, simulation of the entire system were done based on this block diagram, which basically integrate the previously presented mathematical models. One observation is that the load current from the electrical model was obtained from the permanent magnet synchronous generator inverter load curve, which has been also approximated with a 4-degree polynomial. The simulations were performed in the MATLAB Simulink. Now, to compare the experimental and the simulation results, the data from the intelligent relay was acquired directly in MATLAB Simulink using an OPC server, and more exactly KEEP server AX6. This was possible due to the advantage of the intelligent relay of having a viable Ethernet network. Now, in this figure, we can see the computed torque characteristics by the intelligent relay versus theoretical one for different values of the wind speed. In this zoom image, we can observe that with red is the theoretical one, and with blue is the characteristic computed by the intelligent relay. This discretization of the characteristics is due to the sampling rate of the OPC server. Also, we can see interpolated characteristics for wind speed equals with 7.7 meters per second. Now, as we can see, the results are very acceptable. Very low difference are noticeable. So on this slide, you can observe the experimental platform where we have the permanent magnet synchronous generator, which, as I told you, it's identical with the one implemented on the real wind turbine from the Chukot side, which can be observed here. The PMSG is coupled through this gearbox with the induction motor. The induction motor, it's driven by this DTC frequency converter, which is from ABB. The inverter is inside of this cabinet. Now, from the PMSG, the power is injected into the grid using this diode bridge rectifier, which is called a wind interface, and this single phase grid inverter. which are also from the ABB. Here you can observe the intelligent relay, which communicate with the frequency converter, and also the SCADA system, and here, of course, which communicates with the intelligent relay. Also, as you can see, an oscilloscope has been used because or for acquiring the output power of the grid inverter, because this inverter doesn't have communications. Now, let's see some obtained results. So here are a few simulation and experimental results. On the left side, we have the simulations ones, and on the right side are the experimental ones. These were obtained for a cyclic wind speed profile with wind speed between 8 and 9 meters per second. So here you can observe the wind speed. This is the angular shaft speed, the wind turbine produced torque, the permanent magnet synchronous generator torque, and the output power. So if we are compare them, we can see they are almost identical. Next, we have again simulation and experimental results. Simulation here and on this side are experimental, but this time for a variable wind speed profile with wind speed between 5 and 9 meters per second. Again, this is the wind speed, the angular shaft speed, the produced torque by the wind turbine, the generator torque, and the output power. And if we are comparing them, we can see that the results are very good. So these results prove that the intelligent relay can be successfully used for computing the mathematical model of the wind turbine. It's a low-cost solution. This device is around 100 euros. Provide also a free programming software, which is simple to program. It's using function blocks. And also newer version of it provide a small SCADA system that can be implemented on them and to run directly on them, and no necessary additionally desktop is required. Also, due to Ethernet network communication, it is easy to be integrated to other industrial systems, and of course not only with other systems. And I can say that we have this emulator with the intelligent relay over than 3 years, and every time works very well, and it's very easy to start it, and also it's very practical for the students. Now, related to the entire setup of the wind turbine emulator, using a DTC inverter for the induction machine provides the advantages of sensorless torque and speed estimation, which eliminate the transducers. Of course, considering the mentioned inertia and torque compensation to obtain the torque of the permanent magnet synchronous generator. So far, these were the results for the operation of the wind turbine emulator in the first configuration. We will go further to the operation of the wind turbine in the second configuration. As you can see now, the traditional control platform is replaced by the intelligent relay. So is the presented wind turbine emulator, but in this second configuration, where the permanent magnet synchronous generator output power is not directly injected into the AC bus, instead being harvested by this hybrid buck DC-DC converter using at the input a diode bridge rectifier for DC conversion. The hybrid buck DC converter will charge this supercapacitor from which this DC-DC charger will deliver the power into the low voltage DC bus to charge the batteries. Or if the state of charge of the batteries is complete, then the power will be injected through this hybrid inverter into the AC bus. As I told you, this hybrid inverter has 3 output ports and can manage the stored energy in a bidirectional way in relation to the grid and to the local AC loads. Now, here on the left side of the screen, it's the same diagram, but you can observe these two resistors, which are used as protection elements in case of an overvoltage. So for the first case, if the output power of the permanent magnet synchronous generator is greater than the power that can be harvested by the diode bridge rectifier and the HDC, this resistor will be coupled by through this contactor T1. In the other case, in the second case, if for any reasons the HDC will not limit the output power and the voltage on this bus will increase above specific limits, then the R2 resistors will be connected through this T2 switch. So here are a few details about the hybrid buck DC converter. This is a step-down converter obtained from the classical structure of buck DC converter by inserting a simple circuit. We called inductance switching cells in this structure. As you can see, the switching block is formed by two identical inductors, L1 and L2, and two diodes, D1 and D2. On the right side of the screen, you can observe the switching state during T-on and during T-off periods. Now, during the T-on switching period, the inductors, as you can see, are connected in series and the output current is equal to the current through each inductor. During the off period, the inductors are discharged in parallel and the output current is equal with the sum of the current through each inductor. Here are the equations that describe the hybrid buck DC behavior during T-on and of course during T-off periods, of course neglecting the power losses and considering that inductor 1 is equal with inductor 2. Here is the expression of the ratio between the input and output voltages according with the duty cycle. And also here you can see a pictures with the hybrid buck DC converter. More details about these hybrid buck DC converters are presented in part 4 by Professor Octavian Cornea. So the hybrid buck DC converter has been developed to operate with an external reference for the input current, which allows the implementation of the different control strategies without being necessary to modify its internal control. So for this application, the external control was implemented on an identical intelligent relay as the one for the wind turbine emulator, given, of course, the low cost of it. On the previous slide, you can observe an additionally intelligent relay coupled at the command board of the hybrid buck DC converter. So in this figure, you can observe the external control algorithm for the hybrid buck DC converter algorithm, which is implemented in the intelligent relay. The hybrid buck DC converter has digital input and output for the operating state and analog input and output for the input current reference, for the measured input current, and for the input and output voltage. Now, Pressing the intelligent relay F1 button will start or stop the operation of the hybrid buck DC converter. This notation, Q1, Q3, Q4, and so on, represent the digital output of the intelligent relay. Also, the AI5, AI3, AI6, and so on represent the analog input of the intelligent relay, and AQ, 1, 2, or 3, and so on, means the analog output of the intelligent relay. So after the hybrid buck DC converter has started, the input voltage, input current, and output voltage are acquired by the intelligent relay from the HDC. HDC is the hybrid buck DC converter. So first, on the left side, we can see that the input voltage is analyzed, and if its value is greater than 150 volts, the HDC will enter in the state of operating. And if the value is under 120 volts, will be stopped. Also, if the input voltage is greater than 360 volts, the first protection resistors will be coupled. The same behavior related to the output voltage we have. If this output voltage is greater than 90 volts, which means that the supercapacitor is almost fully charged, the second protection resistor will be coupled. Also, these both two resistors can be connected manually, as you can observe here, by pressing F3 button or F4 button. Now, the reference current for the HDC is calculated based on the input voltage and the power load curve, as you can observe here. As for the first configuration, the loading power curve for the permanent magnet synchronous generator was approximated with a third-degree polynomial. So we have the input voltage, which is the input of the polynomial, and the output of the polynomial represent the power that should be harvested from the permanent magnet synchronous generator. This input power from this block is not the same with this input power calculated here. This is calculated from the input voltage and input current and was calculated to be displayed. This is a mistake of notations. So from this calculated required power, the reference input current is determined by dividing the power with the input voltage, and it is prescribed to the HDC. Now, this F2 button, it's used to select if the reference current is prescribed manually from this to C1 up button or C2 down button, or is the result from the power curve. The coefficient for the polynomial related to the power load curve were determined in the MATLAB Simulink. Now let's see some experimental results for the operating of the wind turbine emulator in this second configuration. So here are some experimental results. We have the operation for a cycling wind speed profile with wind speed between 5 and 7 meters per second, and with reference input current provided by the power load curve. Up here is the wind speed profile, and based on the input voltage, the reference current is computed from the power load curve. Here we can observe that the input current follows the reference current. Here are the input and the output power, the difference between them is given, of course, by the hybrid buck DC converter efficiency. And here is the output current, which has a similar allure to the input current, and that's due to the fact that the output voltage is constant. The output voltage is influenced by the DC-DC charger, which injects the power into the low voltage DC bus and of course charge the batteries. In this case, the voltage is constant because the DC-DC charger delivers all the power to the low voltage DC bus. So here is another example with the same operation for the cyclic wind speed profile, but this time with a wind speed between 5 and 9 meters per second to have higher input power. Also, the reference input current is provided by the power load curve. So as you can see, we have higher input power and of course higher output power, but this time the output voltage is not constant because the DC-DC charger has limited the current. So the supercapacitor is charged and discharge according with increasing or decreasing the output power. So for this case, the wind speed profile is variable with a wind speed between 1 and 9 meters per second. Again, it's the same operation with the reference current provided by the power loading curve. What we can observe is that during low wind speed period, the reference current is 0, and that's because the output voltage of the permanent magnet synchronous generator is under 120 volts. Also, the supercapacitor is charged only when the output power of the hybrid buck DC converter is higher than the current limitation of the DC-DC charger. So the previous results were for the, let's say, normal operation when the wind speed is variable and the reference current is prescribed to harvest the maximum power. Now, here is the operation when the wind speed is considered constant to a value of 6.5 meter per second and the reference current is manually prescribed between 5 and 11 amps. So we can observe that the harvested power is accordingly with the prescribed current, but only when the reference current does not produce an input power greater than the available power. For this last case, we can see here that the system will oscillate, and that's because actually the speed of the wind turbine oscillates due to the high load. So protection for this case should be considered, but this example was only to observe the behavior in such conditions. So here we have the same type of operation like previous one for the same current reference interval, but this time wind speed is higher. It's set at 8 meters per second, which means higher input power, which is enough to not have the previous behavior. We can see that the available power is sufficient to cover the requested power, so oscillation in this region doesn't exist. Here are some oscilloscope acquired waveform for the input current versus reference current of the hybrid buck DC converter, only to validate through separate measurement the correctness of the value from the intelligent relay. So with blue, it's the input current, and with red, is the reference current. We can observe that the input follows quite well the reference. So here is another case where the input voltage is measured also to observe the behavior and to validate the acquisitions in the intelligent relay. On the left side of the screen, we can observe if the reference current is too high, the voltage will decrease, or if it's too low, the voltage will increase. On the right side of the screen, the reference current is prescribed from the power load curve, so it can be observed that the voltage and the current have similar allure, which is for normal operation cases. Now, finally, even if the configuration of the wind turbine emulator was different, it was easy to use, offer the same behavior, and facilitate to test of other equipments for a wind turbine conversion system. Now, we will go to the microgrid lab to show you the live operation of the wind turbine emulator, or let's say sort of a live operation, because it is recorded, but I promise you to not modify the record. So, hello again. Here we are in the microgrid laboratory, where I will show you the operation of the wind turbine emulator. But first of all, let me to introduce you to the microgrid lab, a short introduction, and to show you the recording setup in order to better understand of what you will see on this recording. Also, please note that in order to be more realistic, this recording will not suffer any trims. So let's begin. First of all, the device that it's recording me now, it is my phone, and I'm using it because it's offer me the freedom to move. Now it's set on its front camera, but I will switch on the back camera in order to show you the around. So just a moment, please. So as I showed you in the virtual visit, this is the entrance into the lab. On the right side, it is the main distribution cabinet, which is related to the AC bus and to the connection with the national grid. Near it, it is an harmonic active filter compensator, which we are using for different experiments and in different student classes. As you enter in the lab, on the left side, my left side, or on the right side as you enter, it is the repository room. Further are those three workbenches related to the conversion subsystem. And the first one is related to the solar conversion subsystem, which contains the PV panel that are installed on the roof of the building. Also, you can observe the emulator. Here is with red one, it's that inverter that directly inject the power from the high voltage DC bus to the AC bus. Near it is that DC-DC charger that links the high voltage DC bus to the low voltage DC bus, and of course protections and current sensors and others. Near these workbenches in the middle is the workbenches related to the testing of the hybrid DC-DC converter and to verify them for long-term operation. So with some red, you can observe similar or another variant of the hybrid buck DC-DC converter, of that converter that it's used in the second configuration of the wind turbine emulator. Near this converter with green, it's that hybrid bidirectional switch capacitor DC-DC converter which charge those two super capacitor from the high voltage DC bus in order to maintain the level of the bus. Near the converter, you can observe a capacitor bank, which is also used to have more stability of the voltage on the high voltage DC bus. The third workbenches is related to the hydro conversion subsystem. And as you can see the Danfoss inverter. And now it's also a little bit mess because a lot of students are working here. And this workbench we are not using only for hydro conversion subsystem. We are using for other experiments. And right now, as you can see, we have another setup where we are testing and we are developing control strategies for an axially laminated anisotropic rotor reluctant synchronous motor, which is coupled with a classical induction machine. So as you can see, we are using that replacing control board that provide us access to the IGBT's drivers. And together with the space, we are developing different type of control strategies. Also, here on the right side, it is the storage subsystem where you can see those 8 gel batteries, which are here. And there are another set of storage, but this is the main storage of the lab, which is also used as a backup for the main amphitheater on this building. So in this cabinet, just a moment to open it. You can observe the hybrid inverter, which is related to the connection with the AC bus, to the connection with the AC loads, and to the low voltage DC bus. Also, in the right side of this cabinet is the hybrid buck DC-DC converter, which is used in the second configuration of the Winterbind emulator, together with the supercapacitor and with the intelligent relay that it's used for external control for the hybrid buck DC-DC converter, and also the DC-DC charger, which takes the power from the supercapacitor and it delivers to the low voltage DC bus. Now, just a moment to close this cabinet. And we will go to the focus of this recording, which is the fourth workbenches, and which is related to the wind conversion subsystem. So here you can see the Winterbind emulator, which consists from the real permanent magnetic synchronous generator, which is coupled through this gearbox to this induction machine. This asynchronous machine, it's driven by this frequency converter, which receive references from this intelligent relay, on which the mathematical model of the Winterbind is implemented. Also, we will use the Winterbind emulator in the first configuration, in which the power provided by the permanent magnet synchronous generator, it's harvested by this diode bridge rectifier, which is called the wind interface. And further, it's injected into the AC bus using this single-phase grid inverter. Also, here you can see the SCADA system here and up there. And now, related to the recording setup, you can see here a camera that will record the movement of the generator and of the induction machine. Here is another camera which will show you the output power of the inverter, because if you remember, I told you that we don't have communication with the inverter, so I cannot show you the output power in the SCADA system. And of course, my laptop on which I'm using camera management software in order to show you different scene. And also in the lab, we have another, we have other equipments, and a lot of them are also in the repository room. And here, up on this cabinet, are those two resistors, those two protection resistors, in case which are used in the wind turbine emulator in case of a sudden increase above the limit of the voltage on the PMSG side or on the hybrid buck converter side. So now let's start the wind turbine emulator. First of all, I will start the frequency converter. Here you can see inside, this is a 7.5 kilowatts frequency converter from ABB. Now, just a moment to start it. So first of all, let's press the green button. We will wait until it's starting. Okay, and now I will set to be on remote control in order to receive references from the intelligent relay. So for that, here is a letter. L, it's meaning local control, and RAM, which coming from remote, it told us that it's in remote control. And I will start the frequency converter. And now here on the intelligent relay, it has a screen, which was of course developed by us, on which a few parameters are displayed. But because it's difficult to see these parameters on this screen, it has an app that provides us access via a web browser to see these parameters, and I will show you directly on the screen. So just a moment to let my phone, and I will put the phone in order to record what I am doing on this intelligent relay. And now you are seeing the app. So via web browser, what we have to do is only to introduce the IP address of the intelligent relay, and we will have access to the interface. There is also a password and some pop-ups. Okay, so this is the screen of the intelligent relay, and the parameters that are displayed are: this is the wind speed, the set value for the wind speed. This is the angular speed of the wind turbine. This is the torque produced by the wind turbine. This is the reference speed that the intelligent relay is given to the frequency converter. This is the generator torque, and this is the dynamic torque, which is basically the difference between the wind turbine torque and the generator torque. So for this experiment, we will set manually the wind speed. And this procedure can be done as follows. Either directly from this app, in order to press this button, and you see that the wind speed will increase, but it's working with some delay, or directly from the intelligent relay. So now in order to see what it's happened, you can see on the left side of the screen, on the left side up on the screen, it's the screen of the inverter which delivers the power into the AC grid, and there will be the output power. On the left downside is the emulator. Then on the right upside is the interface of the intelligent relay, and on that smaller camera it's to see what I am doing on the intelligent relay. So now I will prescribe a reference speed, let's say 5 and something, maybe 5.5, 5.6, in order to see what it's happened. So I'm only press the up button together with the SC key. So 5.7 should be enough for the moment. Now, as you can see, the grid inverter is in the initialization state because it's receiving power. And it starts, as you can see, to load the generator accordingly, of course, with the power loading curve. So being at the first commissioning of the inverter, it will take a while until it will charge the generator in order to be at the maximum power point. Also, in order to have an idea about the sound in the lab, I will now increase the volume of the microphone, of the camera microphone, which is related or near the emulator. But then I will reduce because you will hear me in echo. So now you can observe that the dynamic torque is negative. That means the generator torque is higher than the torque produced by the wind turbine. And because the inverter will load the generator in order to achieve the maximum power point. And I suppose we are almost at the steady state operation point. So let me to put near the screen with near the intelligent relay screen also the wind turbine characteristic curve to see how it's operates. Just a moment. Okay, so as we can see, the output power is around 630 watts. And let's check the characteristics. So as we can see, here is for 10 meters per second, 9, 8, 7, 6. Here is characteristic for 5 meter per, sorry, now I think you are seeing my mouse. So this is 10, 9, 8, 7, 6, and this will be for the 5. And if we are looking at the wind turbine speed, which is 6.5 radians per second, that means somewhere around here, the power it's probably 600 and something. Let's increase the power. Or let's say not the power, the wind of the speed of the wind. So now you can observe that the wind turbine torque is higher than the generator torque. Or it now are almost equal. The output power is also increased. And now let's see again the characteristics. So the wind turbine speed is around 9.1 radians per second, and at that speed, the wind speed is 7.6, so will be 10, 9, 8, and 7.6 is around here because it's the characteristic that it's interpolated. And 9, we will see that the power should be around 2 kilowatts, but the output power it's 1.7 kilowatts, and that's due to the efficiency, of course. So let's, for example, decrease the wind speed. Let's take given characteristics. Let's set to 6 meter per second wind speed. So of course that the power has decreasing, and let's check again the characteristics. So 10, 9, 8, 7, 6. The wind turbine speed is almost 7 radians per second. That will be some around here. It's nearly here. So the power should be approximately 1 kilowatt. But due to the efficiency, and of course efficiency of the generator, of the dial bridge rectifier, and of the inverter, the output power is 750 watts. So let's increase the wind speed even more. Of course, that wind turbine torque is positive until it's positive. Not the wind turbine torque. The dynamic torque was positive until the wind turbine torque and the generator torque will be equal. So now we have almost 2.9 kilowatts output power. Let's check the characteristics again. Just a moment. So 10, 9, this is the 9 meters per second wind speed characteristics. The wind speed is not the wind speed, sorry, the angular speed of the wind turbine is 11 radians per second. So it's around here, which means 3.5 kilowatts, but due to the efficiency, we have only, of course, only 2.8 kilowatts. Let me check if I can show you the input power. Just a moment. So as you can see, this is the input power, which is almost 3 kilowatts. So considering the efficiency of the inverter, and again, efficiency of the generator, the power it's almost equal with the theoretical power from the characteristics. So now let's reduce the wind speed. Or let me increase and start again the microphone of the camera to hear the noise. Just a moment. And now I'm reducing the wind speed. So now the input power is 0, but you can also see that the inertia is considered and the wind turbine will continue to moving. And also the inertia is considering when the wind turbine start to move. I'll prescribe the wind turbine and you will see that is delayed for increasing in the wind turbine speed due to the inertia, of course. So I will do a few more tests and then I will stop it. Okay, so this is lower wind speed in order to see the operation of it. So let's check again the characteristics. We have the wind speed 4 meters per second. The angular speed of the wind turbine is 4.7. So let's give a... So 10, 9, 8, 7, 6, 5, 4. It is these characteristics. And the wind speed, as I said, it's 4 point, no, not wind speed, angular speed of the wind turbine, it's 4.7, so it's somewhere around here, you see, and the power, of course, is almost 300 or 300 and something watts. Let's see. Some around there, considering, of course, the efficiency, because it's also the efficiency of the gearbox considered. So of course that now the dynamic torque is negative because the generator torque is greater. And now I will stop the system. Just a moment to show you the right camera. And to stop, it's only necessary to press the stop button of the inverter, because the intelligent relay on its on its implementation software, it knows when the inverter is running or not, because when the inverter receives the command to start, the intelligent relay acquire this state, and also do a reset of the integrator to start from 0. So please just a moment to switch the camera. Okay, so this was a short example of the wind turbine operation. Thank you for being interested in this field. I hope it was pretty or was enough for you to understand of its operation. And I will end this recording here, and I will continue with the end of the presentation in the PowerPoint. So see you later on the PowerPoint presentation. Thank you for watching this. So I hope you enjoyed the demonstration of the wind turbine emulator operation from the Microgrid Lab. Finally, here are some relevant references to the presentation. So this was my presentation, and I want to thank you for your attention. What you have seen in all these 5 presentations, in this one made by me and in the others made by my colleagues, it's a part of our teamwork over several years. We are glad to invite you to collaborate with us on common projects and paper, and also even maybe to send PhD students to work with us. And of course, that will be our pleasure to integrate them to the team and to approach common interest topics. So thank you again. I wish you all the best and good luck in your activities. Bye bye.